Now we're getting to the good stuff. Okay, if you want to make a polynomial tangent to a function at a particular x-coordinate, you need the nth derivative of the polynomial at that x-coordinate to equal the nth derivative of the function at that x-coordinate. That's all you need to happen. Now, we're going to start with a generic polynomial. And I need to take some time to make sure you're clear of all that is there. First of all, in the past, you've been taught to write polynomials in descending order. That's going to change here. You want to write your polynomials in ascending order. That means you start with the constant term. That's what C sub 0 is representing. Then you want your first degree term. Now, normally you would write the coefficient of x times x. I want you to think about why I have it written the way I have it written, and I'll come back to that. Then you have your coefficient of your x squared, your coefficient of your x cubed, and so on. And then this is representing the coefficient of the nth degree term. The only thing that differs from one polynomial to the next are those highlighted coefficients. I want you to really take a moment to think about that. Think about all the graphs you've ever seen of polynomials. The only difference from one to the other in their equation are those coefficients. Now, the reason that I have the variable written in the way that I have it written, I could have just written it without the minus a's. But can you think of a good reason for writing it this way if A is the x-coordinate of the tangency? I'm going to have to plug A into each of these functions. Yep, similar to point slope. And if you think about what having an x minus a in an equation does to a graph, it centers it at A. It moves horizontally where your center is. Yep. It's easy to see where x equals a because it's making a bunch of terms 0. And you want to, from now on, think of your polynomials in this manner. Now, like I said, the only difference from one polynomial to the next are those coefficients. So we're going to come up with, ultimately, this formula right here is what we want to figure out. But to get to that point, we need to really think through the math of what is going on. So the first thing we're going to do is find the 0th derivative of P at A and say that's equal to the 0th derivative of F at A. Now, why did I bother saying that? This is the general formula that we are focused on. The 0th derivative means before a derivative is taken, means the function. So this means the same thing as P of A equals F of A. So you've got P of X, replace all your X's with A. What is P of A equal to? Yep. So having this recentered at A allows us to just go, hey, all of these are just zero terms. And P of A has to equal F of A. So what that gives me is, when n is equal to 0, my coefficient C sub 0 is whatever the value of F of A is. And my C sub 0 is just the constant term. Now, we're going to take the derivative of P of X. So I am going to erase, get some of this out of the way. And now just focus on what's there, and let's take the derivative. I'm going to tell you that I see this as a conveyor belt. And the conveyor belt is moving this way. And when I take the derivative, that constant term falls off the conveyor belt. And then the term here, what is its derivative? Just coefficient C sub 1. And then for the next term, when I take the derivative, I'm going to get 2 times blah to the 1 power multiplied by the constant multiple. And then the derivative of x minus a is just 1, so mean. Then next term, we have 3 times blah squared. Derivative of x minus a is just 1, so constant multiple is c sub 3. And then next, 4 times c sub 4, x minus a cubed. And then the general term, n times c sub n, x minus a to the n minus 1. Now I'm going to move to the typed version. Here we go, the typed version. And now that formula that I showed you before that said the nth derivative of p at a has to equal the nth derivative of f at a. I'm now looking at when n is 1. So p prime of plug in a, what does it equal? Oh, shh, quiet, Taya, quiet. You saw it too quickly. Oh, that's funny. It's okay. If I plug a in, all of these terms are just 0. So I just get my constant c sub 1. And that must be equal to f of a. So I've got this ready to type stuff in, and I'm going to then move it around. We found that when n is 0, we have f of 0, or sorry, f of a. Here we have f prime of a. And I'm going to be moving this table to our next round. But first, our next step is to take the derivative again. And again, I'm going to point out the conveyor belt issue. As I take the derivative, the constant term falls off the edge. And then I have 1 times 2 c sub 2, and then that exponent goes down to 0, so it's just times 1. And then I have 2 times my constant multiple, and exponent goes down 1, and then multiply by the exponent, the constant term, and bring the exponent down 1. And now the exponent is n minus 2. Now I'm going to plug in A. And when, oh, sorry, I just realized, silly me. I was thinking about the 1 too early. So if I plug A into every x, because this was set up to recenter at A, all of that's just 0. And I get 2 times c sub 2. The second derivative of my polynomial at A must equal the second derivative of my function at A. So that means that my c sub 2 is the second derivative at A divided by 2. I'm going to bring that into this formula. And now I'm going to move this onward to my typed version. Yeah. And we'll take the derivative from the typed version. So, third derivative. Like a conveyor belt, this moves off the edge into nothingness. And now I have 1 times 2 times 3 times c sub 3, x minus a to the 0 power. Yeah, don't need to write that times 1 issue. And then I continue plus 2 times 3 times 4 times c sub 4, x minus a to the, bring it down 1. And then for the generic term, or the nth degree term, and it magically goes down 1. When I plug a in to my third derivative, I get just the constant term, which is 1 times 2 times 3 times c sub 3. And do you see that the fourth derivative, and by the way, once you hit fourth derivative, you have to do parentheses, write the number, instead of the prime symbols. What do you realize is going to be the fourth derivative of the polynomial at A? It's what's right coming up on that conveyor belt, about to be multiplied by 1. And what does that mean the fifth derivative is going to be? Dun, dun, dun! And the nth derivative Now, let's remember that each of these must be equal to the same derivative order of f at a. And we need to find formulas for our C sub numbers. I love copy paste. What is the formula for C sub n? Do you guys have it? Oh, I remembered I was going to do copy paste. It is the nth derivative at a divided by, you got it, n for n factorial. This is an extremely important formula. And when I say extremely important, I'm underemphasizing. Have any of you run across the phrase Taylor series? Anyone run across the phrase Taylor series? This is what we just found. We just found the Taylor series, but I just need to make it official because that is just the formula for the coefficient of a Taylor series. A Taylor series basically is a way to create a tangent polynomial, although they often don't call them tangent polynomials. That is what they are. And here we go. I want to first of all say that every single term of the polynomial is C sub n times x minus a to the n power. The first n is 0. And we can go as long as we want. Oh gosh, I love 3 blue, 1 brown. They are the best. So wait, did someone I heard it. Oh, yes, hand. Yes.
Why are you solving for C sub n when like the derivative equals the coefficient of C of n, which equals that? I don't know if I'm explaining it, but why are you dividing by the factorials?
We are coming up with a formula for the coefficients of that generic polynomial we began with, and it's multiplying to the factorial. So what we're doing is we're finding out that if we want to create a polynomial tangent to f of x, then, for example, the third derivative of f needs to divide by 3 factorial to find what c sub 3 is, the coefficient of my yeah. And so this is equal to f of x over some domain. I'm just going to put over a domain because I am choosing to deal with domain later rather than right away so that you can see the power of what we are learning and understand just how valuable, or perhaps understand just how valuable this is. Now I'm not done because I need to combine formulas. This is the most important formula on the BC Calculus exam. And did you hear what I just said? This is the most important formula on the entire BC exam. The coefficient formula is the nth derivative at the center divided by n factorial. And that is the formula for Taylor series.